Okay, higher level. We're now going to take a look at these rational functions with quadratics in the numerators, denominators, etc. There will be a fair bit of notes, so make sure to pause this as you need to write all those down, because I will not move at the speed you probably need to do to write notes. So we have looked with standard level at rational functions of linear divided by linear. And sometimes those look quite simple where we don't have all of those terms, but the key feature is that we can write them in this with no quadratic, for example, no e to the x. You may see it straight away where you can identify a x plus b, a is 1 here, or c x plus d. Could be that some things have a coefficient of 0. We're now going to look at a linear divided by a quadratic, which we used partial fraction decomposition to put into a constant over a linear, and we'll see how that applies today as well. Again, that might be missing certain terms, like in this case, d is 0. It could be written in a different order, but always the key feature is that it can be written like this. And we're also going to look at quadratics divided by linears, not just divided by a constant in this case, because then it's just a quadratic. Okay, so do make sure that you can understand and identify what all these look like in all of their different forms, even if things are not quite present in the same way. Let me slide this over so we can see better. Now, for these, we've talked about these key features of rational functions, and these are quite similar. Always, no matter what kind of function you have, rational or not, high-ordered or not, the y-intercept is where x equals 0, and the x-intercept is where y equals 0. And in rational functions, that's where the numerator is 0, because 0 divided by anything except 0 is 0. Vertical asymptotes and horizontal asymptotes, we're going to add on to this today. After simplifying as possible, factoring whatever else, you're going to divide the coefficients of the highest powers, which is really what we were also still seeing with linear divided by linear. We saw that y in the simple ones, if we have ax plus b over cx plus d, we could say that the horizontal asymptote was at a over c. And what I mean in this particular case is if, say, we have something like 2x, I'm actually just going to use b here, cx squared plus dx plus e. The highest power we see here is a squared, so I'm going to have to imagine that there's some number of squared terms here with a 0, and we're going to divide the x squared, okay, which is actually 0. And of course, if you think of if we had the linear on the bottom and the highest power is the quadratic on top, you'd be dividing by 0. So something is going to come up that will make that a little bit different. Okay, here are some examples of that. We have linear divided by linear, we have a linear divided by a quadratic, and we have a quadratic divided by linear to look at here. Y-intercept, we're going to put in where x is 0. When x is 0, in this case, we have that 4 over negative 1 or negative 4. The same thing here, if we put in 0 for the y-intercept in all of these, we get 2 over negative 1, so negative 2. And in this particular case here, if we put in 0, we don't get any, because dividing by 0, there is no y-intercept. X-intercepts is where the numerator equals 0. So when does this equal 0? 0 equals this, subtract 4, divide by 2, at x equals negative a half. Excuse me, negative 2. Okay, if we put in this equals 0 here, we're going to subtract 2 and divide by negative 3. So y equals positive 2/3. And if I want to make this equal 0, you know there are many different ways to solve this. I'm going to use the factoring because I can see there is a nice number that will make it so that it multiplies to negative 5 and adds to 4. Excuse me, positive 4, so these need to be the opposite. And that's when x equals negative 5 and x equals positive 1. So you could have a few different x-intercepts here as well. The vertical asymptote in all of these is where the denominator equals 0. So these can't be simplified in any way. I did make sure of that. We'll see that in just a second. You could look at how these factor out and see if there's a factor in both the numerator and the denominator that you can cancel. But in this case, the vertical asymptote is going to be x equals 1. Always write the equation. When the denominator equals 0 here, well, the denominator is equal to x plus 1, x minus 1. And when does that equal 0? There are going to be two vertical asymptotes. And here we see that at x equals 0, there's going to be a vertical asymptote, which is why there's no y-intercept. Horizontal asymptotes, we're going to look at the highest power. In this case, the highest power of our x terms is a linear. It's to the power of 1. So the coefficients are 2 and 1. So make sure you say that y equals. In this case, you'll see that the highest power here is x squared. The x squared term in this particular one is a plus 0x. That's really difficult to see. And 1. And 0 divided by 1 is 0. Okay. You can write it separately if you'd like. And in this case, the highest power is a square as well. So power of 2. That's 1. And there are 0 x squareds here. Y equals 1 over 0. No. Okay, this is not defined. There is no horizontal asymptote. But now we need to look and see a few new key features because of this. So one of the new key features is discontinuity. Okay, and these are holes in the graph. They're quite hard to see on your calculator. It may not show up. Desmos doesn't do a great job. Wolfram Alpha doesn't do a great job. It is an infinitesimally small point of where this function doesn't actually exist in its original form. So if you can factor and simplify these rational functions, these domain issues that existed in the original function but not in the simplified one just cause discontinuities. Okay, so if you take this original function x minus 1 over x squared minus 1, you'll see that we can cancel out those x minus 1s. And we get something that's essentially equivalent to this function, which is a really simple reciprocal function you've seen before. However, the original function did still have a domain issue at x equals negative 1. So you'll just mark with an open hole that there's a discontinuity there. We have the same issue here, even if it's in the numerator. This is going to be the same thing, just flipped over. So I didn't write it out. You can cancel out the x minus 1s and get that it's basically the same as this linear function. But again, we have a problem here when x is equal to 1. Oops, I think oh, that's right. Okay, when x is equal to negative 1. Interesting, I think this is supposed to be a positive. No, let me write this out. X minus 1, x plus 1. And cancel that out. That's why we get this. But there is still going to be an issue at x equals 1. I actually put my hole in the wrong spot. Okay, so that should actually be constant, and we should have a hole here. Okay, that's the hole with a discontinuity. There's also one more new key feature. If you don't get that you have a horizontal asymptote, you could have an oblique asymptote. So if you have a quadratic divided by a linear, this is where the long division comes in. And you can divide those, but it's not a perfect factor. You're going to get a remainder. And here is this function, x squared plus x minus 2 divided by x plus 3. You'll see that x plus 3 is not a factor of the original quadratic, but we can divide and we get that this is a linear function with a remainder. We are still going to have the vertical asymptote at x equals negative 3, which we can see in the remainder here, right there. But this is going to be the quotient, not the remainder, is going to be the oblique asymptote. The reason being, we never actually can equal this because this is never going to be 0. Okay, so we're always going to be adding something tiny to it. We can get really, really close to it as this gets really big. We get this really close to 0, but it's never actually going to be 0. We will talk more formally about limits going forward, but we're not going to do it just yet. For now, it's worth knowing, though, that what this looks like is that this is the line of an oblique or slant asymptote, diagonal asymptote. You won't have a horizontal asymptote. We still have a vertical asymptote. And it's kind of like we took one of those original reciprocal functions and just kind of squished it. So it's still going to have those two branches as if this had been quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Could be here, but we're going to look at graphing those and exactly where they go in just a second. the easiest way is see, like, we'll have our x-intercepts of these, okay, at -2 and +1. And we'll have the y-intercept here by finding out what will happen when x equals 0. And you'll see it here, and you can do a similar kind of thing and reflect it across like a butterfly. So make sure you take notes on those. Go back, pause as needed. Now, graphing beyond the key features here is just a little bit messy, but it's not terrible. We're going to graph those key features. And what's really important is we had said the asymptotes can't be crossed, but really they just can't be crossed at the ends as we move towards infinity. And then we're going to use test values if needed to fill in any blanks to kind of figure out, especially between vertical asymptotes, what's happening. So as you fill in these kinds of things here, we're going to look for x-intercepts, y-intercepts, and any asymptotes that we can find. In this first one, if you put in, as said, I have them all written down to not waste time, but putting in x equals 0 will give us the y, finding out where the numerator equals that will give us the x. We have our intercept at the origin here. We have vertical asymptotes at x equals 1. And this is because of the factoring. And x equals -3. Okay. We have our horizontal asymptote at y equals 0, because 0 divided by 1. It is weird to say, okay, well, I actually have an intercept on my horizontal asymptote. That's okay, because it's not at the end. It's in this kind of middle area. But now we do need to find out where's the rest of this function. This is not enough information because of this here to figure that out. So you're just going to look around for x values, around the asymptotes, around the intercepts in here, and see where is it going, how is it approaching things. And as you put in some values, like when x equals -1, I get out a -0.5. If I put in -2, I get -4/3. Okay, and you can try as many as you need, but you'll start to see some patterns as you practice these. This is going to look like this. You can see it going up. It could have gone down. You could put in a half and see that it's approaching that vertical asymptote. I also want to look at end behavior here. I want to see, is it down here? Is it up here? Where are those? They're not as symmetric as you have been used to seeing with rather simple reciprocal or more simple rational functions. So do try a few. If I put in -4, which is going to be on this side, I get -8/21, which is a lot less than here. And it can't cross the horizontal asymptote and at the ends here, and it can never cross vertical asymptotes. So it is going to be kind of pigeonholed there. And probably would have helped if I used a different color. I will on the next one. And if I put in 4, I will also get that this is going to be, this was -8/5. That should be here. My +4 is going to be there. Okay. We still get approximately where that is. And this will likely be a sketch, not a full draw. And then over here, we're going to put in values, and we'll see that same idea. It's also going to be in this negative area. Okay, the sketching is fine. As long as the branches are approximately in the same general direction in areas that they should be, then we'll be fine. In this function, we're still going to have the same vertical and horizontal asymptotes because the denominator is still the same. So x equals -3. X equals +1. Okay. We have a y-intercept at y equals 2/3. And I'm now going to use a pencil to make this a little bit more clear of where this is. There it is. We have a horizontal asymptote at y equals 0. 0x²/1x². And now as you graph these and put in some values, again, just testing values, you're going to get that it looks like this. This is just a sketch, right? And testing values here, it will look a little bit different, especially in the middle, because you're not going to have that x value on top affecting negatives and positives in the same way. In this last one, we're going to have that there are x-intercepts at x equals 1 and x equals -3, because these are no longer problems. They're not in the denominator, they're in the numerator. There is no y-intercept, which is a pretty good indication that I probably have my vertical asymptote there, which I do, because dividing by 0 is not possible. And as I find out, well, this is 1 over 0 x squared, that's not possible. So I don't have a horizontal asymptote, but I do have an oblique asymptote. And if you do polynomial long division on this, you get that this equals negative 1/2 x, okay, minus 1. Put this in a spot that's not so clear, so let me do it down here. Negative 1/2 x minus 1. And then we have the remainder of negative 3. Negative 3 divided by negative 2x is going to be 3 over 2x. So this here, the negative 1/2 x minus 1, is going to be the oblique asymptote. And you guys all know how to graph a line. Okay, right here. I could do a few more. Ooh. Okay, the sketch is fine to have this not perfect. And then what you'll see is, here's the asymptote. It's a little bit hard to see. We have this quadrant, this, and this. It can't cross these oblique or horizontal, vertical asymptotes. So it's going to be enough here to sketch this graph. And that's what that will look like. As you can see, this was quite a bit of work though. There is one more nice way. Here's the partial fractions that we talked about again. What you can do in these cases is, this is where you have a linear divided by a quadratic, so no oblique asymptotes, that's quadratic divided by linear. But if you can separate this into partial functions or partial fractions, you can use those to sketch this graph quite nicely. Again, sketching, you can avoid or ignore kind of these scale on the axes, the y-axis especially. If you were to graph these, on the same, this is nice and simple. We looked at this now quite a while ago. Graph these on the same plane. What you'll have is this asymptote here at 1. And I'm just going to do this quite lightly in pencil first, and then I'll go over it with another pen to show what this will actually be. And we have here, I'm going to put them both on the same. So this is the function in red. And here's the function in red as well, negative 4. Sketching is fine. And I'm going to put on the same plane this one as well. So here we have at 1. And in those cases, it will cross the asymptotes. But we're just going to talk through what this will look like, and it is significantly easier to look at it this way. And this is going to go here. I will keep referring to these because they're a little bit more detailed, but you can see in general of where this is. This is still a little bit higher up than this. Okay, so what does this look like when we graph it? You can probably see these emerging. We have to think about which is bigger in magnitude of what's going to happen. If I look here, I will have that this is larger in magnitude than these. These are essentially 0. So I am adding to this very negative branch a little bit of positives, but it's still going to be negative. However, it will just, that's not the pen that works, it will just kind of move it up slightly and make it not quite as strong. But it's still going to be down here. Again, a sketch is enough. Same thing on this branch here. This is going to be a little bit more positive, okay? But you'll see there that it is going to go in the negative area. And it might help you to also think of where the asymptotes are in this particular case. So it is going to go here, and the horizontal 0 is going to be our asymptote, or y equals 0. And here you'll see that this is very positive with a little bit more positive, so it's going to be even steeper if I add these together. I'm subtracting them. That actually changes things slightly. Okay, subtracting, so I'm going to take this negative and make it more negative, but that's fine for now. This negative and subtract this is going to make it more negative. And here I'm going to have this same kind of shape emerging between the axes, or between the asymptotes. Okay, so looking at these and kind of comparing the magnitudes positive and take away a little bit will give us that as well. And you can check the perfect values here, or excuse me, the key features of the asymptotes and the intercepts quite easily. But the general shape is pretty clear on this.